In this video, we will cover a couple of examples using the integral test in order to determine the convergence or the divergence of an infinite series. If you recall in the video about the nth term test, in my video on that, we had an example which looked like this. We had the infinite sum that is often denoted as a harmonic series. It is the sum from 1 to infinity of 1 over n. And using the nth term test, we were not able to determine whether this series converged or diverged, because the limit as n approaches infinity of 1 over n, so of our sequence, was 0. And since it was 0, that meant that we didn't know whether it converged or whether it diverged. In fact, the results were inconclusive. So now we will use the integral test to determine that. So what the integral test does, and if you haven't watched my previous video, I would encourage you to watch that, where I explain what the integral test is. It says that we can take the integral of our whatever is inside of our sum. So that will be 1 over n, and we will make it 1 over x because of convention. And we will take the integral from 1 to infinity. And now if this integral converges, well, so does the series. And if this integral diverges, well, the series does as well. So this is equal to the integral from 1 to infinity of x to the minus 1 dx, which, well, that is, we can't apply the power rule there because we would have 0 and then over 0. So we know that this is equal to, well, that is ln of x from 1 to infinity. Well, we can't necessarily just plug in infinity, so we do the limit as b approaches infinity of ln of b and then minus ln of 1. And this is equal to, well, as the limit as b approaches infinity of ln of b, well, ln of b increases without bound as b or x goes to infinity. So we know that that would equal infinity, and then ln of 1, well, e to the power of 0 is equal to 1, right? We work backwards, so that would equal 0. So we'd have minus 0. And since this equals infinity, well, it diverges. And since the integral diverges, well, we know that the sum does as well. So we know that this sum, the harmonic series, will diverge. And that's pretty neat, right? We used the nth term test and we had an inconclusive result. So then we used another one and it worked. And that's a very common theme that you'll see as you solve infinite series. You will try one test, it may or may not work. You'll try another one, it may or may not work. But you keep on trying tests until you land on one that works. Okay, now in the next example, we will have a series that is very similar to the one before. All we've done is we've raised the exponent. So n equals 1 to infinity of 1 over, now n root n. Okay. Well, we can write the inside, so we'll isolate the inside of this sum, and we will have 1 over n root n, which is equal to 1 over n to the, right, this is 2 over 2, 2 over 2 is 1, times n to the 1/2. And if we add those together, then that is n to the 3/2. And now we can say, okay, well, let's evaluate the integral. Let's do the integral from 1 to infinity of 1 over x to the 3/2. And I think it's important to note that if we had applied the nth term test first to this series, well, we would have had a similar result. Not even similar, we would have had the exact same result as the previous question. We would have gotten 0 because this limit will approach 0 as n approaches infinity. So the results of the nth term test are inconclusive. And we would have to use the integral test now to be able to determine it. So if we take this integral, well, this is equal to the integral from 1 to infinity of x to the minus 3/2 and then dx. So we add 1 and then we divide by it. So if we add negative 3 halves plus 1 is plus 2 over 2, so that equals negative 1 half. So we would get, that would be 1 over negative 1 half, which would be negative 2. So this is equal to negative 2x to the minus 1 half. Now let's just check to make sure we did that right. If we brought this down, multiplied it, well, negative 1 half would cancel out with negative 2, and then we would subtract 1 from the exponent, so minus 1, and we would get minus 3 halves, and yes, we would be back where we started. So now we will evaluate this from 0, or rather from 1 to infinity. And okay, well, we will have to do the limit as b approaches infinity of minus 2, b to the minus 1 half, and then it'll be minus, well, a negative 2 times 1 to the minus 1 half. And this will equal the limit as b approaches infinity of, well, that'll be negative 2 over the square root of b, and then that'll be plus 2. Well, as b approaches infinity, the denominator will increase without bound. And then you will have negative 2 over increasingly large numbers, which will eventually converge to 0. So this will equal 0 plus 2, which equals 2. So thus the integral, the associated integral, converges. It converges, which means that the sum converges as well. So it converges. Now, this is very interesting because let's take a look real quick at the previous, or at the first two examples that we've done. So in this case, we had the sum of, right, we had the sum, let me draw a line here. We had the sum from n equals 1 to infinity of 1 over n. And then we had the sum from n equals 1 to infinity of 1 over n to the 3 halves. And I will write the exponent in the first one just so we can remember that. So we had 1 and 3 halves. And obviously, right, 3 halves is greater than 1. So this sum, we learned it diverged. It diverged. And this sum below, it converged. Converged. And in fact, we can sort of use our intuition that, well, if this sum, right, if this sum is greater than any other sum where the exponent is greater than 3 over 2, right? So if we had some other sum, infinity, n equals 1, and that was 1 over maybe n to the 4th, or maybe it was 1 over n to the 10th. Well, this sum right here would be greater, it would be greater than or equal to the sum below it, right? Because we would, in the bottom, in the one that I wrote on the bottom, that would be less than, because we have a greater denominator and we have the same numerator. Whereas in the top, we would have a smaller denominator because we have a smaller exponent, and we would have the same numerator. So it would mean that all other numbers that are greater than 3 halves, all other exponents that are greater than 3 halves, they would also converge. They would also converge, which means that, well, at somewhere between the exponent of 1 and somewhere between 1 and the exponent of 3 halves, or 1.5, at somewhere between there, it switches between diverging and converging. And this is the beginnings of what we call the p-series. In other words, there is an entire species or genre of infinite series or integrals, associated integrals, that are defined by the integral or the sum of 1 over n to an exponent or x to an exponent. And depending on the value of that exponent, we can quickly determine the convergence or the divergence of the series. And I will cover that information in the next video about p-series and for what values we will immediately be able to determine whether or not the series converges or diverges. If you have any questions, please leave a comment below. I will be sure to get to them in the next video, and I'll see you soon.